Hello and welcome to this FP3 exam paper walkthrough. This was the June 2023 paper with a formula booklet and a calculator. Jumping straight into question number 1, solve the equation this. So here we need to remember that cosh x is e to the x plus e to the minus x over 2. Sinh x is similar, e to the x minus e to the minus x over 2, substitute in and rearrange. So we've got 7 lots of this, 3 lots of this, and then we still have 2 e to the x plus 7 over here. So if I want to simplify this, getting rid of the fractions, make that 2 times bigger, multiply out these brackets, 7e to the x, 7e to the minus x, 3e to the x, 3e minus x. Collecting everything onto one side, we've got minus 4e to the x coming over, so we've got 6e to the x, then we've got 4e to the minus x, minus 14 equals 0, and then a standard trick here is to multiply the whole equation by e to the x, which gives us a quadratic in e to the x. That becomes minus 14 e to the x, and then it cancels with the e to the minus x to give a plus 4 constant on the end. Now as a quadratic I can divide everything by 2, just make that a little bit easier to work with. And then, can we factorize that? I think we probably can. We need a 2, so we've put a minus 2 there and a minus 1 there. I think that is looking good. So 3e to the x must equal 1, or e to the x must equal 2. And then I think, give your answers as simplified natural logarithms. So x is equal to the natural log of 2, and over here x is equal to the natural log of 1/3. Those are our 2 answers for this question. Moving on to question number 2. Part A, determine the inverse of m. So we've got 2, 0, 0, 0, 1, 4, 3 minus 2 minus 3 down here. And we want the inverse matrix. To do that, I need the minors for each element, and I also need the determinant. So let me do that first. That'll give me 3 of the minors. The determinant of m is equal to 2 times by the minor 1, 4 minus 2 minus 3 minus 0. Now I don't need this because it's going to be multiplied by 0, but I will need it for the matrix in a moment anyway. So I'll put it on. Same with this one. 0, 1, 3 minus 2. So I wouldn't normally work those out if we just needed the determinant. We've got 2 lots of minus 3 minus minus 8 is 5. We've got 0 minus 12. And finally 0 minus 3. So that just gives me a 10 there for the determinant. Now the minors, I would normally use m, but the matrix itself is called m. I'll just call it minors. So that's our first 3. We've got 5, minus 12, and minus 3. And then for the 0 in the first column, second row, that would have 0 minus 0. So that's just a 0. And the middle number, the 1, has 2 times minus 3. That's minus 6, minus 0. The 4 has a minus 4 minus 0. There's a minus 4. But that's a 0 minus 0. That gives me another 0 down the bottom here. Now for this one, that gives me 2 times 4 is 8, minus 0 times 0, so that's 8. And the final element here, minus 3, would give me a 2 times a 1 minus 0, so that's a 2. So this is my matrix of minors, and I need to apply the cofactors change of symbols, and that's this. So those with the plus stay the same, and those with the negative change. We've got 5 minus 6, 2 minus 3, 0, all stay the same. 12, 4 minus 8, and of course minus 0 is just 0. Now we need the transpose of that. So our first row becomes our first column. I've done it the wrong way around. First column becomes the first row. You get the same answer. Second column becomes the second row, and the third column becomes the third row. Now we put that together with 1 over the determinant, which was 10, and this is our inverse matrix. And they do not all easily divide by 10, so I will not put that in the matrix, I'll just leave it like that. So that's the inverse matrix for M. Now it says the transformation represented by M maps the plane pi1 to plane pi2. The point xyz on pi1 maps to the point uvw on pi2. So if we've got xyz, applying M on that gives me uvw. Determine xyz in terms of uvw. Now I could do what I've just written on the screen there, and then use what I've got by applying M on this to find this, but that would involve rearranging, because that would give me uvw in terms of xyz, and I want xyz in terms of uvw. So what would be easier, given what we did in part A, is to move this on the other side and use the inverse matrix. Apply that on uvw, and then straight away I get x equals, y equals, and z equals statements. I don't have to rearrange anything. They'll both get you the same answer, but this will be less work. So we're going to apply matrix M, the inverse, onto uvw. xyz is equal to 1 over 10, this thing here, on to uvw. So taking each component in turn, and now I am going to have to multiply by the 1 over 10, so I'll do that as I go, because that's just an easy fraction for each of these. 5u, 0v, 0w, so that's 5 over 10, which is a half u, and there's no v or w for that. That's a nice easy one. The y component, 12u, and then all of these are divided by 10, so that's 6 over 5u minus 6v, so that's 3 over 5, i.e. 6 over 10, and minus 8, so that's minus 4 over 5 w. Then our z term, minus 3 over 10 u plus 4 over 10 v plus 2 over 10 w. And because of the work we've done in part A, that was quite straightforward. Is that all they wanted? Yes. The plane pi1 has equation this. Find the Cartesian equation for pi2. Okay, again, we could go back to this idea here, but because of the way the question's structured, this is quite a nice question. It's leading us through the steps, because from part B we now have x, y, and z in terms of uvw, so we're just going to substitute those in, the expressions that we've got for each of these, into this equation, and we will have the equation for pi2. We'll have to simplify it a bit, but that should be fairly easy. So we've got 3x minus 7y plus 2z equals minus 3. I'll take that down here. And this is part C. So we're going to substitute the expressions on the screen there into this equation. First one nice and easy, 3 over 2u minus 7 lots of, not quite so nice, but still fairly straightforward process, and 2 lots of z, and then we still have the minus 3, and if I grab my calculator, that gives me minus 15 over 2u, and then we've got, with my calculator again, a 5v and 6w. They were much nicer numbers in the end than I expected. We want integers, so we're going to have to multiply everything by 2 to get minus 15u plus 10v plus 12w equals minus 6. And there we go. Part C finished. Question 2 finished. On to question 3. Figure 1 shows a sketch of a curve C with the equation this, a very small part of the curve. Part A showed that the length of C is given by this integral here. For the length of C, we're going to need a formula from the formula booklet. This is in the FP3 section, right at the very back. It gives us S is equal to the integral square root of 1 plus dy by dx, all squared, dx. And of course we're running from the limits given in the question here, pi by 6 to pi by 3. So we've got a bit of manipulation here because we want to differentiate this. So let me just take the function initially and we'll work up to this expression here. Tan x plus a half cot x. And then we want to differentiate this. And if you need these derivatives, I think they're in the P3 section, but they're definitely somewhere in the formula booklet. That's not secant, that's cosecant squared x, like so. And then we need to add 1 to the square of this. Let me square it first. It's looking fairly horrible at this point, but I'm assuming it will all work out. We've got minus 2 of these, so that's 6 squared cos x squared. I don't think I'm going to do this. Let me change this. I'm going to change them back into tan and cot, because we've got an identity that connects secant squared and tan squared. And that will give me a half times 1 plus tan squared if I change that one. This one is similar, 1 plus cot squared. That gives me a half plus a half tan squared minus a half cot squared x. They cancel. So this can also be written as a half tan squared x minus a half cot squared x, which I just prefer, especially given what we're trying to aim at here. Yes, that seems very sensible. Now we're going to square this, and that will give us something not dissimilar to what we were going to get. Minus tan squared x cot squared x plus a quarter cot squared x, nope, power 4 Now what I'm going to do here might seem very strange, but it's just the way that I think about it, because there's a common trick here where you've got something squared minus something squared, and then we're going to add this 1, and it's going to turn into probably something squared plus something squared that matches this original minus expression here. So because I'm expecting it to happen that way, instead of doing what most of you are probably thinking is to cancel these two, because cot squared is of course just 1 divided by tan squared, that would go away. Just the way I'm thinking of it and what I expect to happen, I'm not going to do that. Instead, I'm going to add the 1 from the square root expression here, and I'm going to turn the 1 into a positive tan squared x cot squared x, because I've just realized that I'm missing a half, otherwise that would all cancel out anyway. Yes, I forgot to multiply the halves when I did that, so you get a quarter, but then you get 2 of them, so it's minus a half. And this gives a good demonstration as to why I do it this way, because it lets me see the thing that I'm expecting to see, and if I don't see what I'm expecting to see, it helps me to see mistakes like the one I just made. So when I do the 1 plus dy by dx squared, what I expect is this negative term here to end up being a positive version of the same thing. And when it looks on the surface like that's weird, how can that add together to give me a positive version of the same thing? I go, oh wait, it can, because 1 is the same as tan squared x cot squared x, because they just cancel each other out. And then I've still got all of this other stuff here. But when I minus half of this, of course I have a positive half left over. And if you don't like that, that's fine. You can cancel those instead and do it in a similar but different way. And whichever way you think of it and do it, as long as you follow through correctly, you should end up with the same expression on the next line, which is to factorize this into a perfect square of a half tan squared x plus a half cot squared x squared, which is, as expected, the positive version of this expression here. Now that's great, because all of this work is going into a square root, and that's why I expect something like this, because now when we square root this thing, we get just the bracket without the square. So we've got a half tan squared x plus a half cot squared x, if you can read my writing. And then that goes into the integral and gives us more or less what we're expecting. We just need to pull a half out the front. So s is equal to the integral of half tan squared x plus a half cot squared x dx, pulling the half out and adding our limits, pi by 6, pi by 3, gives us the expression they need in the question. There we go. Part A finished. Part B, by any chance do we have to now evaluate it? Hence, determine the exact length of C, giving your answer in simplest form. Yes, so now we've done all of that. Let's go ahead and integrate. Now, strangely, having said earlier that I like the tan and the cot, and that all worked out nicely, instead of using the secant squared and the cosecant squared here, we're now going to do the exact reverse, because if it comes to integrating, I do not want tan squared and cot squared, and I do want secant squared and cosecant squared, because here, when we integrate these, of course, it just gets us back to these. So now I want secant squared and cosecant squared instead of tan squared, cot squared. So this becomes the integral pi by 6 to pi by 3 of secant squared x minus 1 plus cosecant x squared, squared x minus another 1. So let's just change that, minus 2, rather than rewrite it, just to simplify that. Now secant squared, if we integrate that, we get tan squared, not tan squared, sorry, just tan. And if we integrate cosecant squared, we get negative cot. And negative 2, of course, gives us negative 2x. Pi by 6, pi by 3. If that process wasn't obvious to you, then what I would recommend is you just browse down quickly through the list of integrations and differentiations that you've got in your formula booklet until it becomes clear that these are not easy and these are, not because they are there as an integral, but because they're there as the differential of what we did earlier. But hopefully, given that we did that earlier, that was already in your mind. So now we just need to put the limits in. So we've got a half tan pi by 3 is a root 3 minus a half of cot pi by 3, which of course is 1 over root 3. So that's root 3 over 3 minus 2 lots of pi by 3, but there's another half. Almost forgot that. That's the first one. Minus a half of tan pi by 6, which is root 3 over 3. How convenient, because then cot pi by 6 must be a root 3, and then we've got minus pi by 6. So we've got half of root 3 plus half of root 3 gives us root 3, minus half of 3 root 3 over 3, that's minus root 3 over 3, and then minus pi by 3 plus pi by 6 minus pi by 6. And unless I've made any silly mistakes, that should give us the final answer. Root 3 minus a third root 3 is 2/3 root 3 minus pi by 6. Or if you're particularly keen on single fraction answers, we could put it like that. Either of those is okay. Let me just check that matches anything we were given in the question. We weren't given anything in the question. Okay, let's assume that's correct. Moving on to question 4. Okay, the plane pi1 contains this point here and this vector. Pi2 contains this point and this vector. The line L is the line of intersection of the two planes. Determine a vector equation for L. Okay, this is a fairly standard sort of question. The intersection of pi1 and pi2 means this line is in both planes. If it's in both planes, it must be a direction vector perpendicular to both normals, which means we can take the cross product to find that direction vector. Different ways you can do questions like this, but this is my preferred method. I like my little fish system. For the first component, I've got minus 15 minus 0, so that's minus 15. The middle component is 6 minus 5 is just a 1, and the bottom 0 minus 6. There we go. But we also need a point on that line. So to do this, I'm going to get a general point on both planes. So if we go switching format slightly, I'm going to take the normal vector, minus 1, 3, 3, that dot with x, y, z is equal to the normal dot a point, which is 2, 4, minus 5, and that will give me minus 2 plus 12 minus 15 minus 5, and on the other side minus x plus 3y plus 3z. Now if I do that for the other plane, 2, 0 minus 5 x, y, z, 2, 0 minus 5, and the point 3, 6 minus 2. So that gives 6 plus 0 plus 10, 16, 2x, 0y, minus 5z. Now what I would usually do at this point is to let one of these equal 0, and that's looking tempting on the right hand side to let one of those equal 0, maybe let z equal 0, and then x is 8, yes, actually that looks very nice. I was going to say, but I'm not going to do that because there's no y, so I'll put y equals 0 on the other one and have simultaneous equations in x and z, but if I let z equal 0 here, then x equals 8, and that's really quite nice. So on this side here, if we've got x is equal to 8 and z is equal to 0, and that gives us a really nice number. Okay, that was definitely the right way to go. So one point that will work in both of these is 8, 1, 0, and then our direction vector was minus 15, 1, minus 6, or 15, minus 1, 6, and that is the line L. Okay, that was quite nice in the end for 7 marks. The points C and D both lie on L. Given that C and D are 5 units apart, determine the exact volume of the tetrahedron ABCD. Now you've got to remember, tetrahedron, the volume is 1/6 of the magnitude of the triple scalar product, which is one pair, let's say AB dot AC cross AD, or something like that. Key point being that they're all going to come from one point, and you need 3 vectors here between the 4 points. But to do this, we're going to need the 4 points. We don't have the 4 points, we've only got the 2 points A and B so far. Knowing that C and D are 5 units apart means that we can find relative points, I guess, so it doesn't really matter what we choose as C, so long as we can get D 5 units further down the line. To do that, well, let's make C 8, 1, 0, and then we just need to add enough lambda to get 5 units further down the line for D. To do that, we need to make sure we're using 5. How do we add 5? We're going to have to normalize this direction vector, so we've got 15 squared plus 1 squared plus 6 squared. Hopefully that's a nice square number. It is not. That is 262. Okay, hopefully I have not made a mistake anywhere. But what that means is we're going to want 5 over 262. Sorry, root 262 minus 15, 1 minus 6 added on to point C, and that will give us the position vector of point D, which is really, really horrible. So D is going to be 8 minus 75 over root 262, 1 plus 5 over root 262, and 0 minus 30 over root 262, which does not make me confident that I've done this right, but if you're watching this, I've already checked all the answers, and it is. From here, we've got our 4 points. We already know A and B in the question. C we've chosen to be this, so that D is 5 units using this method. Now we need something kind of like this. What I'm going to do instead, just to make this slightly easier and this D point, is make C my common point. So if I use CA, CB, and CD as my 3 vectors, I'm going to need the points. C is 8, 1, 0. B 3, 6, minus 2. And A 2, 4, minus 5. So C to A, that's A minus C is minus 6, 3, minus 5. C to B, minus 5, 5, and minus 2. And then the point of using C here is that this just gives me minus 75 over root 262, 5 over root 262, minus 30 over root 262. And now I can use the cross product. Sorry, the scalar product. Triple scalar product for the volume as 1 over 6. And definitely putting CD here, not part of the cross product. So let's have minus 6, 3, minus 5, cross minus 5, minus, that's right, minus 5, 5, minus 2. So if we do this, we get for the top element minus 6, minus minus 25, that's 19. Middle element is 25 minus 12, that's 13. And minus 30 minus minus 15 is minus 15. Dot that with the horrible one. Minus 75 over root 262, 5 over root 262, and minus 30 over root 262, and all of that is 1/6. Okay, dotting that gives me minus 1425 plus 65 plus 450. The calculator assures me this is 910, or minus, but it should be modulus. So that becomes 910 over root 262. And when you divide that by 6, you get a really, really horrible answer. So we've got 455 over 3 root 262, and we shouldn't leave a square root in the denominator. And that's no better. It's 455 root 262 divided by 786. So there you go. There's an answer for you. Moving on to question number... Oh no, let's check I finished it. Yes, exact volume of the tetrahedron is this horrible thing here. Volume. Moving on to question number 5. Oh, more matrices. Given that M has a repeated eigenvalue, determine the possible values of K, all the corresponding eigenvalues of M for each value of K. So we've got more than one value of K. Repeated eigenvalue. Okay, to do this we are using the fact that the determinant of A minus lambda I is equal to 0 to determine the eigenvalues, because the information about the eigenvalue is what's going to help us to determine the value of K by the looks of this. So we've got M, oh not A, M in this case. minus lambda I, so we get a minus lambda on the main diagonal. So we've got 1 minus lambda, 2k, minus 1 minus 3 minus lambda, 4, 2, 6, and minus 8 minus lambda, and the determinant of this must equal 0. So following the same process as we did before to find the determinant of a 3 by 3 matrix, we've got the first element times by its minor, which is going to be minus 3 minus lambda times minus 8 minus lambda, that's horrible, minus 4 times 6. Not so horrible. And then we've got minus the second element times by minus 1 times minus 8 minus lambda minus 4 times 2 plus the third element times by minus 1 times 6 minus 2 times minus 3 minus lambda. A lot of negatives in there. What can I do with this? So if I take the minus 1 out of this bracket as a factor in front and out of this bracket, that makes all of these positive. That's a nice change. And then I put this minus 1 here into this bracket. That will make this positive as well. And the minus 2 over here, let's turn that all positive as well. Okay, that's much nicer. Now we've got minus 24 there, and 8, and minus 6 here. Okay, I shouldn't do too much simplifying there. Let's make that equal to 0, and then expand. So we've got all these brackets here. Minus 24 lots of 1 minus lambda, minus 2 lots of 8 plus lambda, plus 16, minus 6k, plus k times 6, so that's another 6k, and then 2 lambda k. Okay, so straight away that cancels, and we're going to have a few more things cancelling, because we've got here a minus 16 minus 2 lambda plus 16. We've got minus 24 plus 24 lambda, and then the 3 bracket expansion. Let's get started on this. 1 minus 3 lambda plus lambda is minus 2 lambda minus lambda squared. Get rid of those. Why have I got a 1 here? That's clearly a 3. Timesing all this by 8, we get 24 minus 16 lambda minus 8 lambda squared. Now times it all by lambda, we get plus 3 lambda minus 2 lambda squared minus lambda cubed minus 24 plus 24 lambda. Minus 2 lambda is actually 22 lambda plus 2 lambda k. More things that cancel, that's what we like to see. So we've got minus lambda cubed, and then we've got 10 lambda squareds. Then we've got 25 minus 16 is 9 lambdas, and this awkward 2 lambda k on the end. Now I never like to have a negative on my first term, so I'm going to change all that. Okay, now normally we would factorize this and get our lambda values, which is kind of what we're going to do, but what we actually want to find is k, and the clue we've been given is that we have a repeated eigenvalue. So well, I've got a lambda in everything first of all, so let's take that out. That's our first value sorted. So that tells us that lambda equals 0 is one of the eigenvalues, which is very useful because either that's a repeated eigenvalue and the lambda will be a lambda squared, or that's not the repeated value and this bracket will be a perfect square in order for that to become a repeated root. Lambda times a bracket squared, then this must be a lambda plus 5, otherwise these two terms here wouldn't come out of that bracket. But when you square this, you get a 25, which is meaning that this thing here must equal 25. So from that we get minus 9 minus 2k must equal 25, which means minus 2k is equal to 34. K is equal to minus 17 is one of our options if our repeated eigenvalue is not 0 but the other one. Or we could have a repeated 0, in which case this bit here must be 0, otherwise you wouldn't be able to factor out another lambda. Lambda plus 10 if minus 9 minus 2k is equal to 0. So that statement is the condition for the lambda being able to factor out once more and giving us a repeated 0 root. And if that's the case, then minus 2k must equal 9, k is equal to minus 4.5. So these are our two k values. And we also need to find the corresponding eigenvalues for each value of k. Okay, we've done almost all the work for this already. If k is minus 17, then this bit here is true, in which case lambda equals 0 is one of them. The other eigenvalue must be the bracket, so lambda plus 5 equals 0, so lambda equals minus 5. And in this case, the minus 5 is the repeated root. The other option on the other side, if 0 is the repeated root, then the other bracket is lambda plus 10, so the other root is minus 10. So on the left, minus 5 is the repeated root, on the right, 0 is the repeated root. Either way, we get two eigenvalues for each of the k values. And that is finished. Make sure it's clear how you set it out, that these two link with this, and these two link with this. The examiner will need that to be clear. Moving on to question 6. The ellipse E has equation this. The point P lies on E. Use calculus to show that an equation of the tangent to E at P is this. There is an equation of the tangent equation that you can remember, but we're using calculus to show this, so we need to go back and do it from scratch. So what we do here, we need to find the gradient, and you can do that in different ways. What I'm going to do here, we've been given x is equal to 4 cos theta, and y is equal to 3 sine theta, so dx by d theta is equal to minus 4 sine theta, dy by d theta is equal to 3 cos theta, and dividing dy by d theta by dx by d theta, we get dy by dx, 3 cos theta over minus 4 sine theta, and that is our gradient, which we can put into our y equals mx plus c equation for the tangent. So that is 3 cos theta over minus 4 sine theta. Oh no, we need a x in there. Now we can use the point P. 4 cos theta is the x-coordinate. We've still got the same gradient. And the y-coordinate at that point is 3 sine theta. Now we can simplify. Can we simplify? Not really. We can get rid of the 4's at least. So let's call this 3 cos squared theta over minus sine theta, but we're going to bring it on the other side. 3 sine theta, and that is equal to c. Now we put that back into our y equation. 3 cos theta x over minus 4 sine theta plus c, 3 sine theta plus 3 cos squared theta over sine theta, and usually this will all simplify quite nicely, which it will because we're trying to find that equation there. Multiply everything by minus 4 sine theta. So we get minus 4y sine theta on the left. This just becomes 3 cos theta x, or if I keep the same format, 3x cos theta. And then we get a minus 12 sine squared theta and a minus 12 cos squared theta. And of course, as is often the case in this type of question, you'll want to factorize that out, and that becomes a 1. So we've got all of this, and then we just need to check we write it in the correct format for what they want. They want the 12 as positive, or everything's positive. So yes, that will work. 12, 3x cos theta plus 4y sine theta, 3x plus 4y, yes. So that's part A finished. Now we need to determine an equation for the normal to E at P. So nothing really has changed here, but instead of using the gradient here, we're going to be using m1, m2 equals minus 1 to get the normal gradient. So if m1 is equal to minus 3 over 4 cos theta over sine theta, is that right? Yes. Then the normal gradient is 4 sine theta over 3 cos theta. And then we do it again. Y is now equal to 4 sine theta over 3 cos theta x plus c. And I've forgotten again, p is 4 cos theta on the x, and 3 sine theta on the y. A bit easier this time because the cos thetas will go, and we'll get 3 sine theta here, and 16 over 3 sine theta here. So we can combine those to give c value of minus 7 sine theta over 3. So our normal equation is 4 sine theta over 3 cos theta x minus 7 sine theta over 3. It didn't give us a particular format to use for that, so I'm not going to bother rearranging. I'll leave it as it is. The tangent to E at P meets the x-axis at point A. The normal to E meets the y-axis at point B. Show that the locus of the midpoint varies with this equation here. Okay, we need to get an expression for the midpoint, which means we need an expression for A and B. A is where the tangent meets the x-axis, so y equals 0 in the tangent equation is the one just at the top of the screen there. So for point A, we want 12 equals 3x cos theta plus 4y sine theta. When y is equal to 0, that's where it meets the x-axis. 12 equals 3x cos theta, so x is equal to 4 over cos theta. For B, we've got the equation on the screen there, 4 sine theta x over 3 cos theta minus 7 over 3 sine theta, and b is where that normal meets the y-axis, so that's when x equals 0, y is equal to minus 7 over 3 sine theta. So this is point A, 4 over cos theta 0, and point B, 0 minus 7 over 3 sine theta. So the midpoint of these two is quite easy because of those zeros. We've got 2 over cos theta and minus 7 over 6 sine theta. Now we need to make that look like equation all the way back up here. X squared p minus qy squared equals r. Okay, to do that we're going to let capital X equal 2 over cos theta, capital Y equal minus 7 over 6 sine theta, so these can vary, and now we need to combine them, but we know that cos squared plus sine squared is equal to 1, so let's rewrite this slightly. 4 over x squared, doing the same over here, gives us sine squared theta equals 36y squared over 49, and then because cos squared plus sine squared is 1, we can add these two expressions together, and it has to equal 1. Tidying it up a bit, make it look like the expression up here. Multiply everything by 49x squared, gives us an x squared here, and a 49 times 4 there, and then rearrange and factorize out the x squared, gives us a 49 minus 36y squared equals 196, and that is in the right format. So r is equal to 196, p is equal to 49, and q, the negative is already in the expression, so q is 36. And that is, I think, the end of the question. Integers to be determined, we have determined, we have finished, and moving on to question number 7. Okay, we're given in cosh to the power n 2x. Show that for n is greater than or equal to 2, in is equal to this thing here. Okay, let's start by splitting this into cosh n minus 1 of 2x times cosh 2x, and then we can use the integration by parts rule, where this is going to be u and this is going to be v prime, because we can integrate that one quite easily and we can differentiate that one quite easily. So the integral of u v prime is equal to uv minus the integral of u prime v. Just to help me out on the side here, v is equal to 1/2 of sinh 2x, and u prime is equal to n minus 1 times cosh of n minus 2x times by the derivative of cosh 2x, which is sinh 2x times 2. A lot going on there. Now put it into the formula. U times v, so that's u, not u prime, cosh n minus 1 2x times 1/2 sinh 2x minus the integral of these two multiplied together, so the half and the 2 cancel out, n minus 1, and we've got sinh 2x twice, so we've got cosh n minus 2x times sinh squared 2x, which is good because we can change that back into cosh squared. Using our identity, sinh squared 2x is equal to cosh squared 2x minus 1. So if we substitute that in there, and I'll also take the n minus 1 at the front, then when we expand that bracket, we get cosh, not cos, cosh n minus 2 times cosh squared gives us cosh n again. And then we get minus 1 times, so we just get cosh n minus 2 dx again. Sorry, not dx. 2x dx. And all this stuff is still on the front. So we've got half cosh n minus 1 2x sinh 2x again. And then this expression in the integral is now what we started with at the very beginning. Oops, too far. Here. So we can change that into the in notation. So this is in minus 2. And then because of what do we want? This is effectively brackets for the in minus 2. So I'll leave that in brackets. That becomes a plus like this. But then we're going to expand this because this will always cancel in this sort of question. Plus in. And we've still got all of this on the front, which I didn't bother writing. Sinh 2x and the in here, which is what cancels with that. And then we bring this term on the left, which is why we end up dividing by n. Still got all of this, sinh 2x plus n minus 1 n minus 2, divide it all by n. We get cosh n minus 1 2x sinh 2x divided by 2n plus n minus 1 over n n minus 2, which I've just assumed matches what they want. Yes. So that's part A done. Now we need to actually evaluate it. Part B, determine, not exactly that obviously, but with a power 3, so expanding this out first. Part B, integral 1 plus cosh 2x cubed, and that will equal the integral 1 plus 3 cosh 2x plus 3 cosh squared 2x plus cosh cubed 2x, which is the integral of 1 plus 3 cosh 2x, and then finishing the integral there, we add 3 lots of I2 plus 1 lot of I3. We can integrate this quite easily. That's x plus 3 over 2 sinh 2x, and then 3 lots of I2. Now we are using the thing at the top of the screen there, which is really horrible. Okay, we've got cosh 2 minus 1, that's just 1, 2x times sinh 2x over 2n, so that's 4, plus, and we still have the 3 on this term as well, 3 times 2 minus 1 is 1, over n is 2, 3 over 2, I n minus 2, and n is 2, so that's I naught, and then back from this expression here, we've still got I3, but I3 is now going to be using this with n equals 3. So we've got cosh 3 minus 1 is 2, sinh 2x over 2 times 3 is 6, plus 3 minus 1 is 2 over 3, I 3 minus 2 is 1. Okay, now we need I0 and I1. I0 is just the integral of this thing with n equals 0. That's just 1. The integral of 1 dx is just x, and I1 is the integral of cosh 2x, which, missed the dx, which is a half sinh 2x. So if we put that in and then simplify a few things, so our original integral, maybe I should rewrite this, 1 plus cosh 2x cubed is equal to x plus 3 over 2 sinh 2x plus 3 over 4 cosh 2x sinh 2x plus 3 over 2 I0, which is x, plus 1/6 of cosh squared 2x sinh 2x plus, sorry, not 3 over 2, 2 over 3 I1, which is a half, so it's now 1 over 3 sinh 2x. Simplifying, we can put our x's together, that's 5 over 2x, and we've got sinh 2x, a third plus 3 over 2, that is 11 over 6 sinh 2x, and then we've got 3/4 sinh, written it the wrong way around, never mind, sinh 2x cosh 2x, but now I'm going to want to write this on the other way as well, sinh 2x cosh squared 2x, and that should be our finished answer. What does it say to do with that? Collecting any terms in your answer. Yes, we did that. Okay, that should be question 7 finished. On to question 8. Okay, starting off with some differentiation. We need to differentiate with respect to x, r cosh 5x. Okay, this is going to be the product rule, so differentiate x, we get 1, and leave r cosh 5x, and then leave x and differentiate r cosh 5x, which I don't carry in my head, but which is on the formula booklet. Okay, it's on the right here, r cosh, I've got 1 over the root of x squared minus 1. So that's x times 1 over the square root of x squared. But it's not x squared, it's 5x squared. So that makes 25x squared minus 1, like that. And then of course we have to multiply by the derivative of the thing inside the function, which in this case is just a 5. So this is the unsimplified version. Let's just put that together. 5x over square root of 25x squared minus 1. And this is the answer to part A. Part B, hence or otherwise, hence means use what you've just done, so this is probably going to be useful. Show that the integral of r cosh 5x, that's this term here, and if we integrate this, obviously we're just going to get back to what we started with, x r cosh 5x. So what we need to do here really is integrate this thing, which we can do, that's fine. Okay, show that the integral, and we've got limits, is equal to this, where we've got a bunch of numbers to find. Okay, so if we integrate both sides of what we've got at the end of part A, x r cosh 5x is equal to the integral of r cosh 5x plus 5x over the root of 25 x squared minus 1 dx. And we can split that integral, so the integral of r cosh 5x plus the integral of 5x, 25x squared minus 1 to the minus a half. And because the 5x is close to the derivative of the thing in the brackets, that is a standard integral. Handwriting getting worse and worse here. So if we integrate this, or what I would actually do if I write this on the side, is consider what would happen if I differentiated this expression here. If I differentiate that, the half would come down the front. I would get 25x squared minus 1 to the minus a half, which matches. And then I would have to multiply by 50x, the derivative of the thing in the brackets. That would cancel, give me 25x, and what I actually want is 5x. So I want 1/5 of this. So that would be 1/5 of 25x squared minus 1 to the power half. Put that in squiggly brackets as an explanation. Therefore, the integral of r cos 5x is equal to the thing on the left, x, r cos 5x, minus this term 1/5 of 25x squared minus 1 to the half. Now if we want the limits, 1/4 to 3/5, 1/4, 3/5, 1/4, 3/5. Now it's just a case of putting it all in, but I do also want to know r cos 5x in terms of logs because of the format here. But again, that's in the formula booklet. So if you look here in the integration section, r cos x over a, where in our case a is a 1 and the x is a 5x, that's equivalent to this expression here. So I'm going to change my r cos 5x into that. So that's x times by the log of 5x plus the square root of x squared, so that's 25x squared in this case, minus a squared is just a 1, and that's all in the log. Then we still have 25x squared minus 1 to the half here. 1/4, 3/5. 3/5 of log 3 plus 2√2 minus 1/5 times by 2√2. It's the first limit, minus 1/4 of log 2 minus 3/20. Throwing everything on the calculator there. And then how do they want this to actually look? We've got the 1/4 log stays as a 1/4 log, but the other log becomes a power. So what was our other log? 3/5. So the 3/5 is going to become a power. We've got minus 1/5 of 2√2 minus 1/4 of log 2 plus 3/20. The quarter log stayed the same, didn't it? Yes, minus 1/4, so r is a 2, and the power and the two numbers inside, p, q, and k. So p is a 3, q is a 2, k is a slightly awkward 3/5, and then we've got minus 2√2 over 5 and plus 3/20. Minus 2√2 over 5 and plus 3/20. Except for the k being a fraction, which is okay because it says rational numbers here. That's worked out quite nicely. So that's our final answer to the final question. I hope that has been helpful for you to go through, and maybe I'll see you in another video.